Hey everybody, Trey here. Welcome back to another video. We're a few days removed from our most recent severe weather event across the Deep South back on Monday, November 20th, and that was our first robust severe weather event in quite some time, but it didn't really live up to expectations. Forecasts called for several significant, potentially long-track tornadoes within the enhanced risk area you see there, but that didn't really come to fruition. We did have several tornadic supercells, but most of them could not consolidate their low-level rotation for any extended period of time, so really the tornado threat was very brief, although we did have a few instances of stronger tornadoes in this event. Still, far from a bust, we're up to 17 tornado reports and nearly 50 severe weather reports in total for this event. And the SPC did a phenomenal job placing that enhanced risk, but the significant tornado portion of the event didn't really come to fruition, so I thought it'd be interesting to do a meteorological breakdown of this event and try to figure out some of the factors that may have modulated the overall tornado threat and kept it from being a more significant outbreak. So without further ado, let's go ahead and get started. Before we dive into the November 20th event, I want to talk briefly about the surprise tornado that we saw in central Arizona, yes, Arizona, on Sunday, November 19th, the day before the Deep South event on the 20th. This is some absolutely incredible footage of a tornado that was rated EF1 outside of Payson, Arizona in the town of Star Valley. Just some absolutely epic footage here, and a very rare sight for Arizona indeed. The impressive thing was that this was from a full-blown supercell just after 9:30 in the morning, so a rare sight for anywhere, especially Arizona. But once we take a look at some of the details here with the environment, you'll see that it was somewhat favorable for supercells. Certainly wouldn't expect this to come out of it, but this was a product of the environment. You can see classic occlusion there, fully occluded mesocyclone there with tornado underneath, just classic supercell structure, certainly a rare sight for Arizona. So let's take a look at the environment here and see what was going on that morning. Taking a look at our 500 millibar map starting at midnight going through the morning of November 19th, you'll see our big trough here that was going to be our main player for the Deep South event on the 20th starting to take shape in the western half of the country. Now, most of the strong flow was still relegated to the backside of the trough, which generally means that the trough is still in a maturing phase. It's still trying to reach peak intensity, but it's not quite there yet. Usually when that flow starts to round the base of the trough into the exit region, that's when the trough will take on a more negative tilt, and you can have your more intense severe weather events in the exit region of those troughs. But when the flow is relegated to the backside of the trough, it's still in a maturing phase. So very broad trough, high amplitude, but very broad trough across the western half of the country, and that flow relegated to the backside. But as we went into the morning hours on the 19th, that belt of strong flow started to overspread much of central and northern Arizona. You see 80 plus knots of flow here across parts of central and northern Arizona. That was going to impart strong deep layer shear into the environment. In this part of the country, we don't have the terrain that we do out to the east to initiate Lee cyclogenesis, where we would have a strong low-level mass response. Of course, in the plains, once that westerly flow traverses the Rockies, you'll get that Lee cyclogenesis process to happen, that low-level cyclone to develop in a much more robust mass response as a result. We don't have that here, so low-level winds were going to remain fairly weak, and as a result, we were going to see very strong deep layer shear in the environment. You see here in our surface map, here is our Payson station right there. Again, Star Valley is just outside of Payson. And you see that the winds remain fairly weak throughout the morning, maybe 5 to 10, 15 knots or so out of the southwest. So when you have 5 to 10 knots of flow out of the southwest at the surface, changing to strong west-northwesterly flow at 80 or so knots, that is very strong change in wind speed and direction with height. And that imparted very strong deep layer shear into the environment. This is not all that uncommon for the desert southwest. Oftentimes in the fall and winter, we'll get these very strong troughs to move through, and as a result, we'll have strong deep layer shear in the environment. What's not all that common is having adequate instability coupled with the strong deep layer shear as these troughs move through. Again, these troughs are very common this time of year in the southwest, across the west coast. So the deep layer shear is often very strong, but we usually don't have enough instability. This, again, is in the middle of November, so we're well removed from any monsoonal moisture, and we often don't have a trigger mechanism to get strong moisture up into central and northern Arizona. The average surface dew point for November 19th at 12Z, which is 6 a.m. Mountain Time, going back all the way in the SPC database, using a bunch of observed soundings from Flagstaff, Arizona, usually runs in the upper teens to the 20s. And you can see here we have dew points in the 30s throughout the morning across the Flagstaff area, Payson even a little bit higher, dew points in the mid 40s or so. So unseasonably high moisture content, that is going to lead to a little bit higher instability. If we take a look at our observed Flagstaff sounding, you can see at 12Z the dew point was 45 degrees. Now that may be a little bit erroneous. You can see this layer here that's has very steep lapse rates. That is probably an error in the weather balloon as it went up. So a little bit erroneous data here, but nonetheless, we still had at least higher low-level moisture than what is typical for this time of year. We'd had a previous shortwave intrusion, some rain a couple days prior to this. That was associated with a little bit higher dew points in the 50s and even low 60s across central Arizona. Some of that made its way up into central and northern Arizona. So we did have a little bit higher moisture content, a little bit colder air aloft as well, coming in from associated with the trough temperatures aloft in the minus 16 to minus 18 degrees Celsius range, which is not super cold, but definitely cool enough to support at least a little bit of instability across the area. And with these strong of kinematics in play, this strong of a wind profile in play, you don't need a ton of instability, just enough to support robust convection, and that's exactly what we got. Going down to 700 millibars, we also see some short waves embedded in the flow. That you see as we go through the progression here, you'll see a little bit of a kink in the height contours making its way into northern Arizona by mid-morning or so. A little bit of a kink there in the height contours, helping to focus the ascent out ahead of it and initiate at least shallow convection across central and northern Arizona on the morning of the 19th. Now let's take a look at some RAP model soundings in proximity to the Star Valley supercell to see what the overall environment looked like. These were taken from the Show Low, Arizona area, which is about 70 miles east of Star Valley and Payson, but the geography and the terrain is very similar, so it should at least be a decent comp for the environment in proximity to the Star Valley supercell. We'll go from 12Z, 5 a.m. Mountain Time, through 17Z, 10 a.m., which is just after the tornado occurred. And I want you to focus on the thermodynamic portion of the diagram, the skew-T portion here on the top left. We start off the day with very minimal instability, and that doesn't change a whole lot throughout the morning. By 17Z, we only had about 100 joules per kilogram of mixed layer CAPE, only about 200 joules per kilogram of surface-based CAPE. So at first glance, you might think that is not supportive of tornadic supercell activity in this environment. And you'd be right. Most tornadic supercell events happen with, 1,000, 2,000, 3,000 plus joules per kilogram of CAPE. So very much on the low side, very low side for tornadic supercell events. But I want you to focus on the vertical distribution of that instability. So if you see here on our skew-T at 17Z from Show Low, you'll notice that even though we only have 100 to 200 joules per kilogram of CAPE, it's all relegated in the lowest 3 kilometers of the atmosphere or so. I mean, look at this. The mixed layer CAPE is 106 joules per kilogram. The 0 to 3 kilometer CAPE is 105 joules per kilogram. So basically all of that mixed layer CAPE is relegated below 3 kilometers in the atmosphere. And as we talked about ad nauseum before on this channel, that helps aid in tornadogenesis in supercells, because if you have any type of spin or low-level shear, that strong low-level instability is going to very efficiently stretch that spin into the vertical and aid in tornadogenesis in any supercells that encounter that low-level instability. So this maybe at first glance, 100 to 200 joules per kilogram of CAPE, that does not really often support tornadic supercells. But certainly when it's all relegated into the lowest couple kilometers of the atmosphere, you can get these low-top shallow storms with very strong low-level instability that can actually produce tornadoes despite very limited CAPE in the quote-unquote deep layer. I mean, if we had 200 joules per kilogram of CAPE spread throughout the lowest 9 or 10 kilometers of the atmosphere, then we'd be talking about a situation where we would not have enough instability to support robust convection that could produce tornadoes. But when all of that instability is in just the lowest couple of kilometers, then you have a situation where you can support low-top convection that can produce tornadoes in the right kinematic environment. And 100 to 200 joules per kilogram is not out of the norm for northern Arizona tornado events. If we take a look at this paper by David Blanchard, who did a lot of work on the Vortex project back in the 90s and a lot of work on tornado events in the plains, he actually was a forecaster at NWS Flagstaff for a time, and he looked at northern Arizona tornado environments. And he actually found, if we go to his figure 4 here, you can see the distribution of CAPE in tornado events that he looked at in northern Arizona. And you can see that really most northern Arizona tornado events are not associated with very strong instability at all. The highest event here that he looked at with the top of the box and whisker plot here, only about 1,200 joules per kilogram of CAPE. And you see the median value here is only about 300 joules per kilogram of CAPE or so, with a lot of this box and whisker plot relegated to the lower portions of the graph. So it's not unheard of to see northern Arizona tornado events occur with only 100, 200 joules per kilogram of CAPE. And so this certainly, even though it looks at first glance, this environment looks at first glance like it would not be supportive of tornadoes because of the limited instability, that is not all that unheard of. When you have such strong kinematics at play and such strong instability in the low levels, you can overcome that deep layer, that lack of overall deep layer instability to produce tornadic supercells in northern Arizona. Speaking of the kinematics, very lengthy photographs indicative of strong deep layer shear, 0 to 6 kilometer shear at about 90 knots. That is very impressive. Now, effective bulk shear, which is the parameter we usually talk about as far as shear goes, is only at 34 knots, which is not all that surprising because effective bulk shear is basically the shear that the storm experiences. And because these storms were so shallow, they're not going to experience all of those 90 knots of 0 to 6 kilometer shear. Effective bulk shear is the shear from the base of the effective inflow layer, so in this case that is the surface, up to about 50% of the equilibrium level, which is where the parcel trace crosses the temperature profile above the level of free convection. If you're not familiar with these sounding terms, go ahead over to my definitive guide to skew-tees and photographs in the playlists tab on this channel. So the effective bulk shear of 34 knots is definitely not all that surprising given the shallowness of these storms, but that is still well within the range for supercells, and any convection, any sustained convection in this environment, albeit shallow, was going to be able to become supercellular given the strong deep layer shear. We had a little bit of low-level shear to work with, some curvature there in the low levels of the photograph indicative of veering winds with height. Only about 60 meters squared per second squared of effective storm relative helicity. If we go up to Winslow, which is to the north of the Payson Star Valley area, you can see we had a little bit more to work with. A little more curvature in the low levels of the photograph, 135 meters squared per second squared of effective storm relative helicity, so certainly well within the range for tornadic supercells, especially in Arizona. We even had some streamwise vorticity to work with. We'll talk about streamwise vorticity a little later in our November 20th analysis, but that streamwise vorticity is when the vector for your storm relative wind, which is from the storm motion to the level of interest of the photograph, and your horizontal vorticity vector, which is perpendicular to the left of the photograph. When those two vectors are parallel, you have streamwise vorticity. And that helps to aid in tornadogenesis in supercells. It's like an NFL quarterback throwing a ball with a perfect spiral. The wide receiver, it's much easier for the wide receiver to catch. He doesn't have to bobble it and manipulate the ball to bring it in and go in for the touchdown. Same thing with streamwise vorticity. That spin at the surface is already oriented the proper way, and when all the storm has to do is ingest it, and then that helps to aid in tornadogenesis in supercells. Cells fired to the west of Payson and Star Valley, which is right here, south of an area of ongoing showers to its north, just before 9 a.m. Mountain Time, about 16Z. You can see the updrafts there, and they immediately start to take on supercell characteristics. You can see the kind of hook shape, the kidney bean shape here with these more robust updrafts. And if we look and zoom in at our reflectivity with our Payson storm, you can just see classic hook echo there, forward flank precipitation here. All in all, a very classic supercell. And as it moves off toward the Star Valley area, it maintains that hook echo very nicely. Just a very well-defined hook, not a very common sight for Arizona standards. And you can see it doesn't have a lot of precipitation associated with it. This is at 9:39 a.m. As the tornado was ongoing, you can still see it maintains that classic kidney bean shape with the hook echo there. All in all, a classic supercell, a low precipitation supercell, not much precipitation with this at all. Maximum reflectivity within the core here, no more than maybe 25 to 30 dBz. So very limited precipitation with this storm. Almost an NP supercell, no precipitation supercell, but a supercell nonetheless. Let's take a look at some velocity data, and you can see right off the bat this storm was rotating. The radar is up here, and the reds are going away from the radar, green's going toward the radar. So very much broad rotation in this storm, pretty much from the get-go. And that continued as it moved off to the east towards Star Valley. And by about 1634Z, 9:34 a.m., you can see an increase in both the outbounds and the inbounds. Those brighter reds and greens are taking shape. That means an increase in the RFD and an increase in the inflow, trying to move toward that balance between outflow and inflow to consummate the tornadogenesis process. And then by 9:39 a.m., that tornadogenesis process was consummated, and you see a pretty tight couplet there in the hook of the supercell. A little bit tough to tell. There are some pixels missing, but you can see the brighter reds and greens there indicative of a tornado vortex signature. That continued on for the next 10 minutes or so. You can even see even as the tornado was dissipating by about 9:49 a.m., a very tight couplet there in the tip of the supercell. A little bit tough to tell, so let's take a look at a product called spectrum width. And spectrum width is basically a measure of the difference in the wind velocities within a single pixel. So as the flow gets more chaotic, i.e. in the vicinity of a tornadic circulation, the spectrum width is going to increase. And you can see as the storm moves off to the east, not much change there in the tip of the hook. Keep your eye on the tip of the hook there. But as we start to see tornadogenesis happen, you see a very stark and sudden increase in spectrum width there, pretty much to the top of the scale, right at the same point as the velocity couplet, and that continued for about 10 minutes or so before dissipating. So this was a fairly long-lived circulation. You can see for at least 3 scans there, we had a heightening in the spectrum width coincident with the tight velocity couplet. So this tornado was in progress for at least 10 minutes or so, which is pretty impressive for Arizona standards. Now let's take a look at correlation coefficients. We can see the debris that was lofted by this tornado. Again, keep your eye on the tip of the hook. Not much going on as the storm moves off to the east until it reaches the Star Valley area. About 9:39 a.m. you see a stark decrease in the overall correlation coefficient coincident with the tornado vortex signature on velocities, indicating a tornado in progress. And again, correlation coefficient, just as a review, is a measure of how correlated the objects are that the radar is bouncing off of. So if it's all rain, you're going to see a correlation coefficient close to 1. But once you start introducing leaves, tree debris, shingles, etc. into the mix, then that correlation is going to decrease and your correlation coefficient will drop, indicating debris being lofted by a tornadic circulation. And we certainly have that here. Very tight debris signature that expands over the next couple of scans. You can see the blues and greens there. It's expanding even more toward the end of the tornado's life cycle, about 9:49 a.m. Very large debris signature here. Not a very tight one, so probably lots of lightweight, loose tree debris. This is, again, the middle of fall, so lots of loose leaves and lightweight other tree debris being lofted, along with the parts of roofs, shingles, etc., being lofted by the tornado. But overall, a very impressive debris signature, especially for Arizona standards, that does dissipate as the tornado ceases. So it was likely the combination of strong deep layer shear to allow those shallow updrafts to become supercells, and the very strong low-level instability helping to really stretch that stronger low-level shear and spin into the vertical to aid in tornadogenesis. You can see the very strong upward motion in this tornado. That is indicative of very strong low-level instability, and that's exactly what we had in this scenario. Just a classic supercell. The question is why this storm, why this updraft and not some of the other ones around it? That's tough to say. There could have been some terrain influences at play. Being from Arizona and having driven through the Payson Star Valley area numerous times, the terrain up there is very complex. Lots of little river valleys, hills, and valleys up there. So there could have been some terrain influence at play, but overall the synoptic environment was certainly favorable for low-topped tornadic supercells, and this is just very impressive for really anywhere, especially Arizona. Very classic looking supercell structure here. You can see the occlusion of the mesocyclone there with the tornado underneath, the clear slot associated with the RFD coming down and wrapping around the mesocyclone. So all in all, just a very classic looking supercell structure for really anywhere, especially for Arizona. All right, let's move on to the November 20th event, the main show across the Deep South. Again, this was far from a bust. We're up to 17 tornado reports in total up to this point, with almost 50 severe weather reports in all. So far from a bust. But again, the significant long-track tornado threat did not really materialize as expected. So first we're going to break down just the overall meteorology of the event, and then we'll go into some of the reasons why this event may have underperformed. We'll start out at 500 millibars at 12Z, 6 a.m. Central Standard Time on November 20th, and you can see that all of that flow that was on the backside of the trough the day before had started to round the base of the trough, and that continued into the afternoon on the 20th, allowing for a strongly sheared environment and strong synoptic scale forcing for ascent across that Texas, Louisiana, Mississippi, Arkansas corridor. We also had strong defluence aloft across the Deep South. As we talk about often on this channel, defluence is the spreading apart of the winds in the upper levels of the atmosphere. That creates a void, and to fill that void, air is brought up from below, and that is how we get large-scale rising motion for storm development in a given environment. We can better diagnose this at 300 millibars, and as we take a look at our 300 millibar map here, over Arkansas we can see a little bit more of a southwesterly component to the flow, whereas closer to the Gulf Coast the winds had a more westerly component, so definitely those winds were spreading apart in the upper levels of the atmosphere, helping to create that synoptic scale forcing for ascent for storm development across Texas, Louisiana, and Mississippi. The 500 millibar trough also maintained a positive tilt throughout the day. As we've talked about before, while positively tilted troughs can produce robust severe weather, most of your significant tornado outbreaks are associated with negatively tilted troughs. I won't go too deep into this right now, as we're going to revisit this in a little bit, but certainly this event was associated with a positively tilted trough, and that was the case throughout much of the day. Still a very potent trough, providing the necessary ingredients for a robust severe weather event. As you might expect, with the strong upper-level trough with westerly or southwesterly flow traversing the Rockies, we had surface low development somewhere in the Oklahoma Panhandle vicinity on the 19th, and it moved off to the east-southeast to a position along the Red River by the morning of the 20th. It continued to move off to the east-southeast during the day on the 20th to a position somewhere in East Texas, the Louisiana border region. Was not a very tightly wound surface low, and we'll come back to that in just a little bit, but a surface low nonetheless with several important features that aided in the progression of the overall setup. Zooming in on our raw surface data at 12Z, 6 a.m. Central Time on November 20th, you can see we had not yet had robust moisture return across much of Louisiana, those 60s dew points hovering on or just off of the southern Louisiana coast, and that was due to very much east-southeasterly surface winds helping to pump that moisture into East Texas instead of much of Louisiana. You can see here across East Texas, we had robust moisture return underway, mid to upper 60s dew points across much of East and Southeast Texas. As that surface low moved off to the east-southeast, the winds across Louisiana would veer somewhat to more out of the south, allowing that moisture northward, and we would undergo rapid moisture advection as we went into the early afternoon hours there. You see those dew points making their way up into the mid to upper 60s by about midday as storms were beginning to fire. Dew points in the mid to upper 60s there, even 70s there across southwest Louisiana. As that moisture return became much more rapid, those surface winds had strengthened and veered a little bit, which in this case was good, as the trajectory of the moisture return was a little bit better to get it up into the Louisiana area out ahead of the surface low and cold front. Speaking of the cold front, let's draw in our surface low and attendant surface features. This is at 19Z, about 1 p.m. Central Standard Time, so right as storms were percolating across East Texas into western Louisiana. First of all, we note this somewhat loose cyclonic or counterclockwise circulation across southeast Oklahoma, so we can place our surface low center somewhere in this vicinity. As for our cold front, we see a clear wind shift from central into east Texas. Winds across north central and central Texas out of the west, switching to more of a southwesterly flow across east Texas. So a clear evidence of a wind shift there, and so our cold front probably is going to go somewhere in this vicinity here. Our warm front is a little bit more tricky to draw in and to identify. Across Arkansas, we have winds out of the east switching to more of a southwesterly and even southerly flow across north central and central Louisiana. We see a clear temperature gradient across this area as well. Temperatures in the 70s and even 80s across central Louisiana, switching to 60s and 70s across north central Louisiana. So I would personally place our warm front somewhere in here, certainly more so on the diffuse side at this point. It would become a little bit more well-defined later on, but at this point it was quite diffuse. But just as a rough guide, I'd put our warm front somewhere in that vicinity there. We can also draw in another feature, and that is a confluence band or prefrontal trough out in the open warm sector. This was predicted well by models. You can see here, just ahead of the cold front, winds were more out of the southwest, switching to more southerly or southeasterly flow across the Texas-Louisiana border region. This was clear evidence of a prefrontal trough or confluence band somewhere in that vicinity there, and that was likely our initiating boundary for storms across East Texas that would eventually move into Louisiana. Jumping ahead to about 22Z, our surface features had become a little bit easier to identify. Our surface low was located somewhere in the Arklatex vicinity. Our cold front was still draped down to the south and southwest. Our wind shift associated with that cold front had maintained itself. Winds out of the west across much of East Texas, more southerly flow across Louisiana, so our cold front was probably draped somewhere in this vicinity here at this time. Our warm front was also easier to identify. Temperatures in the 70s, even low 80s across central Louisiana into southwest Mississippi, temperatures in the 60s across northern Louisiana. We'd had some early convection along and north of the warm front that had reinforced the position of that warm front. So if we were to draw in our warm front at this time, it'd probably be somewhere in this vicinity here, draped to the east across northern Louisiana, and then to the east-northeast across western Mississippi. We're going to revisit this warm front orientation in a little bit, as it may or may not have played a role in the evolution of the event. And we may have even started the occlusion process with the surface low where the northern portion of the cold front catches up to the warm front. But for now, this is a good assessment of the surface pattern at this time, which is again about 22Z, about 4 p.m., as some of these supercells were getting going across central Louisiana. Going into the evening hours, the robust moisture return continued, 70s dew points maintained across southern Mississippi into southern Louisiana, so any ongoing supercells were able to continue to take advantage of a very moist low-level environment, despite the loss of surface heating as the sun went down. Back up at 850 millibars, there was a low-level jet in place throughout much of the day from East Texas through the southeast states, about 20 to 30 plus knots or so across Texas into Louisiana, and that did increase going into the evening hours to about 30 to 40 knots across Louisiana and Mississippi. Storms began to fire fairly early on in the event, between about 7 and 9 a.m. across East Texas. They didn't do a whole lot until they got to the Texas-Louisiana border region and into western Louisiana, at which point reflectivities began to increase and the severity of the storms began to increase as well. Now, there was some concern in the days leading up to the event that there would be quite a bit of cloud cover across the warm sector to help thwart the growth of instability. But that certainly was not the case. As we take a look at visible satellite here, you'll notice, you can see those bubbly cumulus in East Texas representative of the developing storms. And there were quite a few cloud breaks in the vicinity of those storms, as well as out ahead of these storms across northern Louisiana. We were sitting in the Ruston area, which is along I-20 in the northern part of the state, awaiting these storms to head our way. And this was our view. We were seeing pretty much pure blue skies, very few clouds to deal with. And so the instability issue did not look like it was going to be an issue. Very rarely have I seen a sky like this on the morning of a southeast severe weather event when I've been out chasing. So this was very promising, but this can also be a double-edged sword. This strong surface heating, of course, can allow instability to grow, but it can also induce vertical mixing. Vertical mixing, we've talked about before on the channel, is when you have strong surface heating that allows the air near the surface to rise, but that can also bring down air from above down to the surface. And if you have a little bit of drier air up here, that drier air can mix down to the surface, helping to decrease low-level moisture and overall can negate the severe threat. And we're going to talk a little bit more about this in a bit when we do our sounding analysis. But mixing did not appear to be an issue in this case because we had such strong low-level warm moist advection that would continue to bring that strong low-level moisture into the region and help offset any mixing that would take place due to the strong surface heating. The storm mode was quite complex. We had a mix of clusters and several semi-discrete supercells moving through central Louisiana into Mississippi. You can see a couple back here coming out of East Texas into west central Louisiana, and the main one was really this one that originated back here near the Jasper, Texas area and tracked all the way through central Louisiana, producing a brief tornado before it crossed Interstate 49, and then moved off to the east into eastern Louisiana, where we intercepted it from the town of Archie to Faraday. We even took some large hail in the town of Faraday. And then it moved into southwest Mississippi, where it produced several brief tornadoes as it approached the I-55 corridor. You can see the classic supercell shape there. We're going to take a closer look at this storm in just a little bit, as this was really the main supercell of the day. But there were some other supercells as well, and the storm mode really was able to at least stay somewhat semi-discrete. They're, again, somewhat messy given the abundance of precipitation and some of these clusters in here. But we were able to maintain several semi-discrete supercells in this environment. We also had a bunch of little warm advection showers that just couldn't quite take hold. They just couldn't become robust. And we'll touch on that in a little bit as well. But overall, the storm mode was not super prohibitive to long-track supercells with a tornado threat. All right, let's get into some of the factors that may have caused this event to underperform. Now, I know that wasn't a full deep dive into the meteorology behind this event, but we're going to fill in some of those gaps as we go through some of these possible failure modes. Now, once again, we've been able to establish that we had several semi-discrete long-track supercells, but they were not able to produce significant long-track tornadoes. So there must be some inhibiting factors at play that reduce the overall significant tornado threat with those storms. And the first one we're going to talk about is the progression of the 500 millibar trough. In the days leading up to this event, the trough was expected to take on a much more neutral or less positive tilt with time on the 20th, leading to a slightly more robust severe weather threat and the significant tornado threat. But that didn't end up happening. So we're going to take a look at some model data from the days leading up to this event and then compare those to the actual progression of the 500 millibar trough using our SPC mesoanalysis to see why the subtle difference in how the trough actually progressed may have slightly negated the overall significant tornado threat. Now let's quickly review what the tilt of a trough actually means. The tilt of a trough simply refers to the orientation of the axis of the trough, indicated by the dashed blue lines you see in the examples here. A positively tilted trough has an axis that tilts toward the right, while a negatively tilted trough has an axis that tilts back toward the left. This has some implications on the overall environment. A negatively tilted trough tends to mean your trough is closer to maturity, or in other words, your trough is a little bit stronger than when you have a positively tilted trough. This induces a couple of things. Number one, a negatively tilted trough tends to be associated with stronger differential temperature advection in the vertical, meaning stronger cold air advection in the mid and upper levels of the atmosphere and stronger warm air advection in the low levels. That creates stronger instability. And number two, as we've talked about on this channel before, what happens in the mid and upper levels of the atmosphere influences what happens in the low levels of the atmosphere. So a stronger trough aloft often leads to more divergence aloft, which corresponds to more convergence at the surface, and that leads to a stronger cyclone in the low levels. That means a couple of things. Number one, your surface low is going to be more intense, meaning stronger, more backed flow out ahead of that surface low. And your low-level jet tends to be stronger. Your low-level cyclone is going to be stronger, so the wind field out ahead of that cyclone is going to be stronger as well. That creates stronger wind shear both in the deep layer and in the low levels. So most of your robust tornado events are associated with a negatively tilted trough. That's not to say with a positively tilted trough that we can't have robust tornado events. We've had plenty of significant tornado outbreaks in the past associated with positively tilted troughs. But the less positively tilted your trough is, i.e. the more negatively tilted your trough is, the more robust the tornado threat tends to be, and more of your robust tornado events tend to occur with less positively tilted, more negatively tilted troughs. All right, let's take a look at some model data. So this is the 12Z NAM from November 19th. So the NAM run on the morning of the day before the Deep South event. Again, we're looking at 500 millibars, and the time and date are up here in the top right, so you can follow along there. As we talked about, the trough took shape across the western half of the country, started to dig down into the southern plains. Very much a positively tilted trough through much of the day on the 20th. You can see the axis here looks something like that, very much a positively tilted trough. But watch what happens as we go into the late afternoon and early evening hours, especially across the Arctotex northward. The trough continues eastward, but it takes on a little bit more of a neutral tilt. We almost see a separate little shortwave start to develop within the flow, a little bit of a kink in the height contours there with a much more neutral tilt than what we saw earlier with our main trough. That continued into the overnight hours. This was expected to be basically the height of the event, basically the late afternoon, early evening hours, as this trough took on a little bit more of a negative tilt, and that continued into the overnight hours, early morning hours of the 21st, very much a more neutrally tilted trough at this point. Even our little shortwave here across the Ohio River Valley taking on a slight negative tilt, helping to tilt the overall trough a little bit more neutrally. Here's another model. This is the 12Z HER from November 20th, so the morning of the actual event. You'd think by this point the models would have started picking up on some of those potential changes in the progression of the trough, but that certainly was not the case. So here's our trough, continues to move east throughout the day. And you'll see as we go into the late afternoon and early evening hours, that shortwave develops as we saw on the NAM. With this model, it's even more exaggerated. You see the little kink in the height contours there, certainly a neutrally to slightly negatively tilted shortwave within the main trough. This is at 2Z, 8 p.m. Central Time, certainly supposed to be at the height of the event, and that would continue into the evening hours. That shortwave took on a little bit, even more of a negative tilt, helping to orient the entire trough more neutrally tilted, and that shortwave certainly negatively tilted as it moved into the Ohio River Valley. Okay, let's compare those model runs to what actually happened using our SPC mesoanalysis. Again, we're at 500 millibars, and we'll start at 12Z on the 20th and go through the duration of the event. So here's our trough ejecting into the southern plains, and you'll notice that as we go into the late afternoon and early evening hours, we never really developed that shortwave that we saw on the NAM and the HER runs. Here we are at 2Z, 8 p.m. Central Time, and you see we don't really have that shortwave that developed here across the Arctotex northward. Still a very much positively tilted trough here, and that was very different from what the model showed. Just going back to the 12Z HER on the 20th, you'll see at 2Z, very well-defined shortwave within the flow, the entire trough starting to reorient itself to more neutrally tilted. That certainly was not the case with what actually happened. The trough maintained its positive tilt, and we never really developed that notable shortwave within the flow to help reorient the trough as a whole to more neutrally or slightly negatively tilted. We really only developed a little bit more neutral tilt to the trough very late in the period. This is at 7Z, so into the early morning hours on the 21st, well after the peak of the event, you start to see the trough finally reorient itself a little bit more neutrally tilted, but still, this was well after the tornado threat had subsided, and this was supposed to happen much earlier, and we actually, during the event, maintained more of a positive tilt trough, and of course that has implications on the low-level flow. Here we are back with our 12Z NAM from November 19th. Then we're looking at the surface now. Surface low develops in the Oklahoma Panhandle vicinity on the 19th, slowly drifts off to the east-southeast during the day on the 20th. You'll notice it is somewhat of a broad circulation here, but we do see a little bit of a tightening of that surface low toward early evening across the Arkansas-Louisiana corridor, coincident with the upper level trough taking on a more negative tilt. Now here's our SPC mesoanalysis data at the surface starting at 12Z on the 20th, going through the duration of the event. Surface low starts the day in southwest Oklahoma, basically along the Red River, meanders off to the southeast through the day, and you'll notice we don't really see a consolidation of that surface low, just remains a broad circulation as we go through the afternoon into the early evening. Here we are at 2Z, 8 p.m. Central Time, and you'll see not even a closed contour here across the deep south, just a very broad disorganized circulation. Compare that to what we saw on the NAM. This is at 3Z, so an hour later, but still very comparable, and you'll see a couple of closed contours there. So a slightly tighter, slightly more intense surface low. Again, it's a subtle difference, but it's an important difference nonetheless. With this type of solution here is what the models were showing. We have stronger, more backed flow in the warm sector, slightly stronger deep layer shear, favorable for more significant tornadoes. We compare this to what we saw here, much more disorganized surface flow as we zoom into our raw data, much more disorganized, much weaker surface flow, leading to weaker low-level shear, not quite as favorable for significant tornadoes. Same thing with our low-level jet at 850 millibars. This again is the 12Z NAM from November 19th. We'll start at 21Z, 3 p.m. Central Time on November 20th, and we'll just go through the early evening. The low-level jet was expected to decrease a little bit during the day, although models were still progging a little bit of an enhanced plume of low-level jet from East Texas into Louisiana, 30 to 40 knots at most. But then by early evening, the low-level jet was expected to ramp up pretty significantly as the low-level cyclone intensified, coincident with the upper-level trough taking on a slightly more negative tilt. 40 to 50 knots of low-level jet here across Louisiana and Mississippi by 0Z, 6 p.m. And then going into the evening hours, 3Z, we saw a very stark increase in the modeled low-level jet, especially centered on Mississippi, 50 to 60 knots of flow there at 850 millibars. However, as you might expect, that's not exactly what happened. Throughout much of the day, the low-level jet sat around 20 to 30 knots from eastern Texas into Louisiana, and we did see an increase in the low-level jet going into the late afternoon and early evening hours to about 30 to 40 knots across south-central Mississippi into southern Louisiana. Certainly an increase from what we saw during the day, but not nearly as strong as what was expected. As you recall, we saw about 50 to 60 knots as modeled on the NAM there across much of Mississippi, and the flow across Mississippi at 850 millibars didn't really increase above 40 knots throughout the duration of the event. So the slightly less robust low-level response led to a less robust low-level jet. Certainly an environment still favorable for tornadoes, but perhaps not significant long-track tornadoes. And we're going to dive a little bit more into the overall wind profiles in the atmosphere as we go through our sounding analysis next. Before we dive into the full sounding analysis, let's take a look at some vertical wind profiles from across the region. So, as I said, we were up north stationed in Ruston, Louisiana, awaiting storm intensification, and I pulled up the Fort Polk, Louisiana VWP, and this is what I saw. Just after noon, this is what we saw. And again, a VWP, vertical wind profile, is basically, we can estimate the wind profile in the atmosphere from the radar. The radar, of course, scans wind velocities, so we can take the wind velocities at every level and come up with a hodograph at that location. Again, this is at Fort Polk, southwest of Alexandria, Louisiana, just after noon Central Time. And I was very surprised to see this kind of hodograph. You can see very large looping hodographs here, strong shear in the low levels of the hodograph. 0 to 1 kilometer storm relativity above 300 meters squared per second squared. So very, very long hodographs, and I was not expecting to see this early in the day. As we talked about earlier, the low-level shear was expected to remain fairly weak throughout much of the day until late afternoon, early evening, when the low-level jet was expected to intensify. This was just an hour and a half later at 1947Z, just before 2 p.m. Central Time, and much of the same, very strong low-level shear, over almost 400 meters squared per second squared of 0 to 1 kilometer SRH, over 550 meters squared per second squared of storm relative felicity. That is extremely impressive. That indicates a strong deep layer shear for supercells, as well as strong low-level shear for tornadic activity. Of course, this coincided with the time that the environment was still trying to prime itself, trying to destabilize fully as the storms were moving out of East Texas into western Louisiana. Now, this is what happened as we went later on in the day. This is at Jackson, Mississippi, just before 6 p.m. Central Time, as the supercells were moving out of eastern Louisiana into southwest Mississippi. Notice what happens there. This was a hodograph just before 2 p.m. This is what we saw to the east at 6 p.m. Definitely a significant decrease in low-level shear. Very limited curvature there in the low level. Still some low-level shear, but certainly not what we had anticipated with the strengthening of the low-level jet that was expected to happen going toward late afternoon and early evening. We were expecting very large looping hodographs that would increase in size going later on into the evening, and that did not appear to be the case. Lengthy hodographs, strong deep layer shear, but very limited curvature here in the low levels, indicative of a weaker low-level jet than what was expected, and that was very surprising to see. So this certainly is not typical southeast outbreak type shear, which might look something like this, where you have very strong low-level shear, strong veering of the winds with height, and large looping hodographs. Not what we were seeing here, and so kind of instead of the profiles becoming better with time, they actually seem to degrade a little bit with time as far as a significant tornado type of environment went. Of course, this is still favorable for tornadoes, but these kinds of hodographs here with more limited low-level curvature tend to foster more cyclic supercells with briefer tornadoes rather than something like this, which we saw earlier, and in our typical southeast tornado outbreaks in which you have very large low-level shear, which favors more steady state, long track tornadic activity. All right, let's now take a look at some RAP model proximity soundings from across the region. We'll take a look at a set of soundings from Alexandria, Louisiana, which is a good proxy for the environment, sort of in the western half of the risk area when the storms move out of East Texas into western Louisiana. And then we'll take a look at some soundings from Jackson, Mississippi, which is a good proxy for the eastern portion of the environment as the storms moved out of Louisiana into Mississippi. We'll also insert some soundings from the Macomb, Mississippi area, which was south of the ongoing activity because Jackson became a little bit convectively contaminated toward the end of the period. So we'll take a look at some Macomb, Mississippi soundings to kind of get a clearer picture once the Jackson soundings become a little bit contaminated. We'll also look at some observed soundings as well. We'll start off with our Alexandria soundings at 12Z on November 20th. We start off the day very much outside of the warm sector, just 57/49 at the surface. Some drier air aloft, and I've heard this theory thrown around a little bit as far as a failure mode for this event. We'll talk about that in just a little bit. But we do see a moistening both in the low levels and throughout the entire atmosphere going into the afternoon hours. You see here the dew point really climbs, the temperature at the surface climbs as well as we get that sunshine, that continued warm moist advection. By about 20 Z or so, we're fully destabilized, about 1,200 joules per kilogram of mixed layer CAPE, 80/65 at the surface, slightly well-mixed boundary layer there, given all the sunshine in place, but fully destabilized here. And at this time, the storms were moving into central Louisiana and taking advantage of some somewhat increasing low-level shear. And this may be slightly underdone from what we saw with our radar VWPs just earlier, but at least some curvature in the low levels of the hodograph, about over 170 meters squared per second squared effective storm relative helicity, some veering of those low-level winds with height. So we're fully destabilized at this point, some curvature in the low levels, certainly favorable for tornadic activity, perhaps though not significant long-track tornadic activity. This is more favorable for more cyclic, brief tornadic activity, given somewhat limited low-level shear, adequate but limited low-level shear, but we're fully destabilized here. And as we go into the late afternoon and early evening hours, we stay fully destabilized as the low-level shear increases. And then as the cold front approaches, the wind profiles become a little bit wonky. The surface and low-level winds veer a little bit, and the hodographs straighten out. But we're still able to obtain enough low-level shear going into the late afternoon, early evening hours to support continued tornadic activity. We had a supercell near Marksville that actually produced probably the longest track tornado of the outbreak, over 20 miles in path length. But again, keep in mind that we're fully destabilized here with adequate low-level shear. All right, let's go to Jackson, Mississippi now. Much of the same to start the day, 54/47 at the surface, so well outside of the warm sector at this point. But that changes pretty quickly going into the afternoon hours. We start to see a very deep moist layer. You see by 20Z, 2 p.m. Central Time, our moist layer is extremely deep, up to about 700 millibars. We're starting to destabilize a little bit, very much a layer of dry air aloft here, and again, we'll come back to that in just a second. But we continue to destabilize, and by about 23Z, we're fully destabilized here at Jackson, Mississippi. Now, at this point, the sounding started to become a little bit contaminated, so we're going to go down to Macomb, Mississippi. Note that we're fully destabilized, about 700 joules per kilogram of mixed layer CAPE here at Jackson at 23Z, 5 p.m. Central Time. and our wind profiles were starting to improve a little bit, even if this might be a slight overestimation based on what we saw with our VWPs. So let's go down to the Macomb, Mississippi soundings, just south of the Jackson, Mississippi area. So once again, fully destabilized here, about 1,200 joules per kilogram of mixed layer CAPE, 76/68 at the surface at 23Z, and a nice looking hodograph there, strongly veering winds with height over 250 meters squared per second squared of effective storm relative velocity. But keep your eye on the 700 millibar level here. Watch what happens with the thermodynamic profile. We start to see an introduction of a warm nose there at 700 millibars, and it persists going into the evening hours here. You see at 2Z, 8 p.m. Central Time, and we have this very stout warm nose here. Despite a very deep moist layer in the low levels beneath that capping inversion, but that capping inversion starts to work its way in pretty quickly going into the early evening hours, even though low-level shear is increasing with time. So we kind of had this catch-22 situation as the storms were moving out of Louisiana into Mississippi. We had the low-level shear profiles that were increasing with time, but this cap was also increasing with time, and it reminds me a lot of the May 20th, 2019 high risk across northwest Texas into Oklahoma. We had the stage set for a very much a historic tornado outbreak, but the little bit of a warm nose or capping inversion started to work its way in at about 700 millibars throughout the afternoon, and that helped to, number one, thwart warm sector supercell development, and number two, limit the intensity and longevity of the supercells that were producing tornadoes coming out of northwest Texas into southwest Oklahoma. Same thing appears to be going on here. So to the west, back at Alexandria, we had a fully destabilized environment throughout the entirety of the event. So we had supercells that were able to move into this environment. Even though the low-level shear was decreasing with time, they were still able to produce tornadoes, including that one I told you about near Marksville, which was on the ground for at least a decent amount of time. Fully destabilized, mature supercells able to thrive in this environment. As they moved into southwest Mississippi, they were able to continue, and of course we've talked about this before, even though we can have a capping inversion, if we have strong low-level shear, that can help overcome some of the capping inversion. But this may have overall limited the intensity of these updrafts and limited the overall threat for significant long-track tornadoes, and instead kept them a little bit on the weaker side and more brief side. So very interesting here, and you can even see it on the 700 millibar map. So this is our 700 millibar map from SPC mesoanalysis, and these red dashed lines here are our isotherms, lines of equal temperature. Keep your eyes focused here on the Louisiana-Mississippi corridor. You're going to start to see a little bit of a ridging in the isotherms as we go on into the afternoon hours. You'll see it starts to show up right about now. You'll start to see a little bit of ridging over Louisiana, and that means a warming of the mid-level air over this area. And that continues to build as we go into the late afternoon, early evening hours. This is at 2Z, and you see a very, very nice thermal ridge there. Those isotherms bow upward, meaning a warming, again, of the mid-level air across Louisiana and Mississippi at 700 millibars. So that is indicative of some sort of capping inversion working its way in, some sort of warm layer working its way in across this area. What are the hypotheses for why this occurred? Well, number one, notice how the flow throughout much of the day at 700 millibars was out of the west-southwest, right into this Louisiana, Mississippi. Well, we trace that back all the way into central Mexico off the central Mexican plateau. Could be some sort of remnant elevated mixed layer making its way off the higher terrain here of western Mexico, finally making its way into Louisiana and Mississippi. As we saw on the May 20th, 2019 event, we had a nice little EML make its way northward and kind of thwart things across northwest Texas and southwest Oklahoma. Could be a very similar situation here. But because we see this thermal ridge just sort of develop out of nowhere, instead of us seeing a thermal ridge out here that is translated off to the east, we see this kind of develop over Louisiana and Mississippi in the late afternoon hours. That could be a result of convective processes. And I won't go too deep into this because that is beyond the scope of this video, but we could have, again, we had a lot of convection here that may have warmed the mid-level environment just a little bit, and that could have allowed the mid-level air to warm just a tad, just enough to thwart the overall intensity of these supercells. So again, kind of a catch-22 situation. Back to the west at Alexandria, we had a fully destabilized environment, but decreasing low-level shear with time. those supercells moved into Mississippi, we had increasing low-level shear with time, although albeit it started a little bit on the weaker side, weaker than what was expected, but increasing low-level shear with time, but increasing capping with time as that warm layer worked itself in. Still, we were able to maintain mature supercells because we had deep moisture, strong low-level shear, and we've talked about many times before how strong low-level shear can compensate a little bit for less than ideal thermodynamics in the low to mid-levels. We've seen that in cases like Greensburg, Kansas, and many, many others. But this warm nose, this is not just a tiny warm nose, something like that. This is a pretty stout warm nose here. And that certainly, at least in my opinion, worked to decrease the intensity of the overall supercells and may have played a role in the lack of significant tornadoes in this environment. Let's talk about the dry air now. You can really see it in some of the observed soundings from across the region. Here we are at Shreveport, 12Z observed sounding, ample dry air aloft there. 12Z at Lake Charles, lots of dry air aloft there. You could really see the dry air with southern extent in this setup. 18Z Lake Charles, we had really deep in the moist layer, extremely deep moist layer, but atop that, ample dry air. 21Z at New Orleans, much of the same, deep moist layer, but lots of dry air above that. 0Z at New Orleans, pretty consistent with what we saw throughout the day. You can even see some evidence of that capping inversion starting to work its way in around 700 millibars. So what impact did this dry air have on the event? Probably not a whole lot for the more robust supercells off to the north across central Louisiana and southwest Mississippi. Perhaps a little bit of dry air got mixed into the rear flank downdrafts, which leads to evaporative cooling. Evaporative cooling leads to stronger downdrafts, and perhaps a tendency for those RFDs to undercut the mesocyclone or tornadic circulations more efficiently than if there were more moist air in the mid and upper levels of the atmosphere. But where it really took a toll was these discrete beans coming off the Gulf across southern Louisiana into southern Mississippi. When you have these smaller updrafts, they really have a tough time surviving if there's a lot of drier air in the environment. We've talked about the concept of entrainment before on the channel. Entrainment basically is when updrafts are sucking in air from the outside, and when that air is dry, that can do some pretty significant damage to those updrafts and really decrease the overall robustness and intensity of the updrafts. Really, in these environments, when there's a lot of dry air or when there's a strong shear in play, when you really need updrafts to cluster together, at least initially, in order to survive that initial time when they're growing and then be able to sustain themselves later on. For example, these northern supercells, a lot more clustered updrafts, still able to maintain a semi-discrete storm mode up there, but you can see a lot of different updrafts around here. So the supercells, when they were younger, were able to resist the drier air in the environment, resist that strong deep layer shear, and were able to survive because they had their friends, so to speak, around them to help them grow and become mature supercells. Down here, we just have a bunch of these little pockmarked updrafts all across the area, really not clustered together in any fashion, so they have a tough time sustaining themselves with such dry air in the mid and upper levels of the environment and such strong shear. You can see they really just don't do much. Really, the main activity was confined up here to central Louisiana into southwest Mississippi, and those discrete beans to the south really were never able to become anything. And that capping inversion at 700 millibars coming into play, smaller, younger updrafts can't really withstand that capping inversion, while the more robust supercells, as we know, can withstand that cap to some degree. To wrap up this video, I just want to discuss the evolution of the main supercell of the day. This was the one that tracked from near Jasper, Texas into central Louisiana, produced a tornado near the town of Colfax, moved into eastern Louisiana where we intercepted it as it produced large hail, and then it moved off into south central Mississippi and produced tornadoes once again near the I-55 corridor. Really, this was the main supercell of the day, the one that really was the longest track supercell of the day and would have had the opportunity to produce significant long track tornadoes, but because of the aforementioned reasons may not have been able to get a chance to do so. So this storm initiated well back into East Texas, southwest of Jasper. You see the convection coming out of the bottom left corner of your screen. Good evidence of that clustering effect that I talked about just a little bit ago. These updrafts will tend to cluster together, and that helps them resist any dry air entrainment or that strong wind shear that's available in the environment. These little isolated cells have a tendency to get shredded apart by dry air entrainment by the strong shear, but when they can cluster like this, that allows them to band together sort of until one becomes dominant, at which point you can have a robust, more mature supercell. And that's exactly what happened here. That clustering kind of persisted for a little while until it crossed into western Louisiana, at which point we got a mature well-defined supercell to the southwest of Hornbeck, west of Anacoco, continued to move off to the northeast and get organized. You see the strong reflectivity gradient on the forward flank of this storm, indicative of the supercell processes starting to take shape. Continued to move off to the northeast, and at which point it started producing tornadoes. Classic hook shape here on radar. Tornadoes began happening as it approached the I-49 corridor in central Louisiana. And so at this point, it was producing tornadoes. Very strong rear flank downdraft. You can even see it here on radar, this little appendage sticking out from the tip of the hook. Here is your hook echo, or RFD, draped down to the south and southwest. As we talked about before, perhaps a little bit of that dry air was getting entrained into the rear flank downdrafts of these supercells, as they appeared to be very aggressive in surging outward, undercutting any potential tornadic circulations for quite a while. And that was, again, a possible deterrent to significant long-track tornadoes in this event. Moving our radar view a little bit off to the east, here's our main supercell. And as we talked about, most of the discrete beams coming out of southern Louisiana were unable to sustain themselves, except for a couple that began to interact with the ongoing supercells, particularly this one that moved west of Alexandria. And this one began to take a supercell shape all on its own. You see here our ongoing supercell going through a reorganization phase. This new little bean taking on its own supercell shape, nice hook, kidney bean type shape there, on a crash course with the forward flank of the ongoing supercell. So I thought, when we were out chasing, I thought once this merger happens, this might be tornado time. And it started to reorganize itself. It started to develop a new mesocyclone, new hook echo. The inflow to the storm started to increase dramatically, and I thought, here we go, here's our significant tornado. But it was really never able to wrap up its low-level rotation. It continued to move off toward the northeast. We were driving along ahead of it, right in the notch of the storm, really. So we had a great view back into the hook echo of the storm. And I wasn't able to take pictures, unfortunately, because I was driving. But from a visual perspective, there was really nothing that screamed significant tornado producer. It was very much, it had that look of a shelf cloud, not really any area of defined, well-organized low-level rotation. It just didn't look like a storm that was going to produce a significant tornado. So we continued to stay ahead of it, and we intercepted the storm in the town of Faraday, where we took significant hail. Here's some of my video from in the town of Faraday, and you can see that we were bombarded by some pretty large hail, especially for southeast standards. Most of this was half-dollar size hail. I'll play it again. Most of this was half-dollar size hail, maybe a few stones that were slightly bigger. But if you watched my forecast video for this event, I said I'd be very surprised if we saw large hail out of any supercell across Louisiana and Mississippi, especially because the low-level shear was expected to be so strong. Strong low-level shear tends to inhibit the hail production processes, the large hail production processes in supercells. So the question is, why was this storm able to produce large hail? It was tornadic earlier. Now it had transitioned to producing large hail instead. So one hypothesis is that the storm merger may have initiated large hail production with this supercell. If you add, storms with more mass tend to produce larger hail. In other words, when you have a storm merger, you're adding mass to a storm, so that storm may have a greater chance of producing large hail. So if we rewind our radar here, you see once the merger happens, we start to see a little bit of a bump up in the core here. Not a very significant bump, but perhaps a slight increase in the overall reflectivity within the core. Doesn't last terribly long, goes away a little bit, and then it starts to really ramp up as it closes in on Faraday. Extremely strong reflectivity within the core there, as well as in the hook. We were in the hook echo of the storm in Faraday, and we were still receiving very large hail. I wonder how large the hail was here up toward the Clayton area within the actual core. So the merger could have initiated large hail production in this storm, although the initial merger happened well before this stark increase in the reflectivities in the core and the resultant increase in the hail size. So the merger may not have been a direct cause of the large hail production with this storm. It also may have become elevated for a brief period of time. Started off as surface-based in central Louisiana as it produced those tornadoes nearing the I-49 corridor. Then it moved off into eastern Louisiana, started producing hail, so it may have run into some unfavorable thermodynamics and become elevated above the surface. What's that going to do? Well, as we said, stronger low-level shear tends to favor tornado production in right-moving supercells. So for example, if you have something that looks like this, strongly curved low-level hodograph, strong low-level shear, that is going to favor tornado production in supercells. But if your storm is rooted above the surface, above that strong low-level shear, the storm is not going to feel all of this strong low-level shear. Instead, it's going to feel whatever's above that level at which it's based. So the hodograph, the effective hodograph, if you will, is going to be much straighter. The low-level shear, quote unquote, the storm is feeling is much weaker than the actual ambient low-level shear. And therefore, in weaker low-level shear environments, large hail production is favored. So if the storm was elevated, it would tend to produce large hail instead of tornadoes because it is rooted above that strong low-level shear layer near the surface. So the storm continued to produce hail as it crossed the Mississippi River. We'll switch over to the Jackson radar here. And it started to get its act back together as it approached the I-55 corridor, started to regain that hook echo, and the trail storm actually started to intensify as well. And that began to take over and become the dominant storm, almost acting in sort of a bookend vortex type fashion. The old storm up here, the new supercell down here, and this third hook echo from a little bean merging into the complex there. That image of the three hooks, if you will, was shared quite widely on social media. But this southern supercell was the one that took over, started producing tornadoes after it crossed I-55, and continued to do so for quite a while. Brief tornadoes, but continued to produce tornadoes, perhaps becoming surface-based once again. And then the trail storm once again took over, kind of merged into a little band there, and then the trail storm kind of took over and began producing tornadoes, brief tornadoes once again near the McGee area, after which point the tornadic activity stopped. So a very interesting evolution with this main supercell. So that's going to wrap things up for this video. I know it was a long one, but this was a really interesting event, and I think going over the failure mode cases, even though this was far from a bust, is oftentimes more important than going over the successful forecasts. So hopefully you learned something about what made this setup tick and what kind of held it back from being a more significant long track tornado outbreak. Still, again, far from a bust. 17 tornado reports is what seems to be the number that's been settled on. So 17 tornado reports across the area, some damaging wind reports, and some large hail reports, which was not expected. Certainly I was surprised when we got some large hail there in Faraday with that main supercell. So a very interesting event. Hopefully you learned something from this video. Thanks for watching, and we'll see you in the next one.